Now, let's have the concept of accumulation points. We have here the definition. We let A be any, set A be any subset of the set of real numbers. Then, a point P, which is a real number, is an accumulation point of the set A if this is satisfied, wherein for any open set G that has an element P, it implies that if we get the intersection of the set A to the open set G minus point P, then it has point in common. Now notice here in the definition of the accumulation point, P is any real number. It's not the same case in our previous discussion as of the open set, wherein P is strictly in the set A. But here, for the accumulation point, P could any be point. It could be in the set A or it could not be in the set A as long as it is a real number. So we have here the notation for the derived set of A, which is the set of accumulation points of A. So let's have this example. Let's try to consider this set. This is the set 1, 1/2, 1/3, 1/4, 1/5, so on. Actually, this is just equal to the set 1 over n, where n is any real number. So let's try to consider this geometric representation of the given set. This is the given set, and this is the geometric representation. So as you can see, the set has decreasing elements. So from 1, 1/2 to 1/2, 1/3, and so on. So as you can see, the elements in this set approach to 0. Now in this case, notice here that the elements going to 0 are very close to each other compared to the set from 1. Here, medyo si 1 is medyo not closer to 1/2. Now to test for the accumulation point, we need to satisfy this one. We need to show this one that for any real number P, and we have here any open set G that contains a point P, or that contains a real number P, then there is a point in common if we get the intersection of the set A to the set G minus P. So we will take any point. It could be in A or not in A. So for the point, say, let's have here point P, which is equal to 1. Okay, let's try to show if it satisfies. Intersection G minus, this becomes 1 minus na. So where is G here? So we can have any open set G. So any possible na open set of open set G. Here we can take G here, which contains 1.1, or we could have G as long as any open set rather that contains 1. So pwede diha, pwede this one, or very small open set as long as it contains 1. Now if notice that our elements here, itong 1, 1/2, 1/3 are elements in A. So if we are going to take the intersection of this open set minus this one, we get 1 here. So is there a point in common to this set and this set minus 1? Okay, the answer is no point in common. Therefore, the intersection is empty. Hence, we can say that 1 here is not an accumulation point. So 1 is not an accumulation point. Now let's try another number. Any real number. Say which is not in A. So what number is that? Let's have here 2. So 2 is there. Or let's have negative 1 rather. Negative 1. Say for example we have here, let's have here negative 1. Okay, negative 1. So any point G, any set rather G. So it could be bigger set or smaller set as long as it contains negative 1. So let's try to get their intersection if it satisfies. So here, this set, this is G, our G, intersection to these elements is, of course, there's no point in common. So, empty set. Hence, negative 1 is not an accumulation point of A. Now, as you observed here, if we will try to get any point here, any point here, here, because as you noticed, the elements in the set in this side here medyo not closer to each other, right? So if we take this and then get open set G and then minus this one intersection, still the result is empty set. There is no point in common. The same thing if we take this one or any point between 1/3 and 1/2, here, a point here, any point between 1/4 and 1/3 or 1/3 mismo or 1/4. If we take, say, any open set G that contains this point, eto, and then intersection nimo sa A, notice ang A nato is kana lang ng mga points. Pag kuha nimo, if you get the intersection of it, there's no point in common. So, still, the intersection is empty. Now, you try to analyze here. Notice that the points here, the elements in the set A are getting closer to 0. So, try to imagine elements here getting closer to 0. They are very close to each other na. They are very close to each other na here to 0. Now, if we are trying to pick P as 0 here, 0, and then we will get any point, any set G that contains 0. Notice here any point in G. Now, any set G, open set that contains 0, pwede dito, bigger set, or you can make it as very small kay para kunuhay nga minus nimo no point in common. Pero still, though if you're going to make this smaller set small enough that contains 0, still there is an element here in A because we know that the elements in A are getting closer to 0. So, bisa pagpagamyan pa na nimo maayos di open set na G, nagyo mag-exist diha nga element ni A. Okay. Most of the elements in A are getting closer to 0, or it approached to 0. The elements approach to 0. Therefore, if we are to take the intersection of A to G minus 0 here, there is an element in common, right? Because, again, getting closer naman ni siya to 0 ang mga elements ni A. Kani, mga elements ni A pa doon dito, getting closer to 0. So, as n approaches infinity, si A sub n pa, si kanipod si ang elements, si P, mo-approach po siya sa 0, where P is an element of A, or any, say, Q na siya, or Q. Mo-approach po siya sa 0, as N approaches infinity. So, here, bisag, pagamihan ninyo mo si open set nga G, para, kumbaga, minus ni mo ang 0, gusto ni mga walay common element ni A, still, naghapoy common kay closer naman ang mga elements niya to 0. So here, it's not empty. So there is an element in common. So we can say that 0 is an accumulation point. Accumulation point of A. So by investigation, we can say that the derived set of A, which is this one, the derived set of A is equal to 0.0. So that's it. Let's consider another example. Let's have this set B. So we will show the intersection of the set B and the open set G minus point P is not equal to empty set. Now first, if it is in this set, the set is in interval notation, so we will try the boundary points. We have here 1 and 4. So let's take P equal to 1. So let's try to show if what's the intersection of B and any set G minus 1. Okay, now based from this geometric representation, we have 1 here, so we can take any open set G as long as it contains 1. So we can make it smaller enough. So let's have this one. So this is our G. Now notice that if we are going to get the intersection of this set to G minus 1, we will get this one. We'll remove 1. So as you can see, the intersection of this smaller set to this set, notice that our A is here, from here to here. Close, and then open. Notice that the intersection of G, this set, and this set is not empty, right? Not empty. There exists here an element that is common to the two sets. Therefore, this is not empty. Now let's have here point P. Say here point P. Let's take again another open set G here, and we will get the intersection of B, this set here B, to the smaller set here G minus 0.4. So we will remove 0.4. Since this is an open interval, the set B is an open interval, still there exists an element here that is common to both this set and this set, even if we remove this point here. Therefore, this is still not equal to empty set. And if we try to get any element here, like for example, let's have here, here is 2. So still, if we get the open set G, and then we take the intersection of the set here, this set, to this set, removing 2, still you can get the common element. There is a common element. And so with this, and any point here in between 1 and 4. But if we get, say for example, 5 here, as you can see, if we let P equals 5, so we get the open set G here, and the intersection to this set minus this one is, there is no point in common. Therefore, 5 is not an accumulation point, right? But because it satisfies here, 1 is an accumulation point. So with 4 is an accumulation point. Also, the points in between 1 and 4 are also accumulation points. But 5 is not, and the other way. So beyond this set, from 1 to 4, or between, including 1 and 4, they are all accumulation points. Beyond that one, the point is not an accumulation point. Therefore, the derived set is the closed interval from 1 to 4. So take note, 1 is an accumulation point. So 1 is included here. So with 4 and the points in between 1 and 4. Now, if we consider this set here, the set of rational numbers, why is that the accumulation or the derived set is the set of real numbers? So, we will have a geometric representation for this. So, consider the real number line here. We know that the set of real numbers is equal to the union of the rational numbers and the irrational numbers. Now, try to imagine, if we have here the set of the real number line, the rational numbers are very close to each other. Just like, for example, if we have here 0.01, of course, 0.001 is also a rational number. 0.001, 0.0101 is a real number, real and irrational number. So, as you can see, the rational numbers are very close to each other. Very close to each other. And the irrational number, the irrational number, they are all real numbers. Now, if we are to consider any point P in R, any point P here, and then we will show Q intersection any set G minus any point P, any real number. The answer is there a point in common? So let's take here P. Hatang P. Say, we will get here an open set, open interval G. You can make it very small because rational numbers are very close to each other. Even if we remove this P here, this point here, and then we will get the intersection of it in the set of rational numbers, still you can get a point in common, right? There is a point in common here to the set of rational numbers and the open interval G minus P. So this is not empty. There is always a point in common to both sets because the rational numbers are very close to each other. Even if you get here P, and then you get the opposite here. So since it is very close to each other ang rational numbers, and then we remove nimo si P, intersection din ka sa Q o sa set G, removing P, still there is a point in common. Any real number will do. It could be P be a rational number or an irrational number. Okay? Therefore, we can say that the derived set of the rational number is any real number. So it is R, the set of real numbers. It means you can have any real number. All real numbers are accumulation points of the rational number. So let's have another example here. Let's have the set of natural number. Now for the set of natural number, let's have this illustration here. For the set of natural number, we have here 1, 2, 3, and 4. Now, if we are to take 1 as our P or any point here, okay, anyway, P is a real number man. You can have 1 or 1.5 or 1.1. So, consider that as our P. So, if we are going to get an open set here, and then i-intersection na nimo sa 1, 2, 3, 4, which is our N, minus na nimo og P, the intersection is empty. Follow? Intersection is empty. There is no point in common. Nga naman, our N is 1, 2, 3, 4. They are not closer to each other, right? And if we are going to make our open set G be smaller enough, we can do it. Smaller enough nga kung i-intersect nato ni si G minus P to N, to the natural number, there is no point in common. Hence, this is empty. Therefore, by the way, if we are going to take any point here, say for example 2, kung ano to si 2, still magkuha tag open set diri. Sorry, magkuha tag open set diri ni 2. So, pag intersect nato ni N, minus 2, still, there is no point in common. Isa pag diri ka makuha sa 2.5, okay, why? Because you can make the set G smaller enough. Si 2.5 here. So, ang atong G na to, diha, dili maabot sa 2, 3. Ang open set. Minus mo si 2.5, the intersection is still empty. Therefore, any point here, any real number, is not an accumulation point of N. Not an accumulation. Therefore, the derived set of N is empty. Again, if we have this one, the real number line, we have here 1, 2, 3, 4, and so on. Let's try to consider the set of natural numbers. 3, 1, 2, 3, 4, and so on. Now, if we will take P equals 1, so if we will get here set G, and then we remove 1, this is G minus 1, removing 1 here, this one, and then the intersection mo siya sa 1, 2, 3, 4, and so on, set N na to, the intersection is empty. There is no point in common, right? Okay, 1, 2, 3, 4 man na ito ang set G diha. And then, if we will take, say for example, 2.5 na lang na to. 2.5, say, we have 2.5 here. We can make G small enough. So, any open set G that contains 2.5. So, if we are, again, to take the intersection of N, this is N, 1, 2, 3, 4, to G minus 2.5, still the intersection is empty. Hence, 1 is not an accumulation point of N. Also, 2.5 is not an accumulation point of N. Or any number here, any real number, is not an accumulation point of N. Therefore, there is no accumulation point of N. Hence, the derived set of N is what? Is empty.